Our first step is to find the equation that will give us the force exerted by the water on the plate. This equation will also tell us the parameters that will be necessary to calculate the force. Pressure is equals force over area. Solving for the force, we have force is equals pressure times the area. For the US system, pressure is defined as delta times the depth. And if we substitute that into the original equation, we have that force is equals delta times the depth times the area of the object. This was the image given in the book. First, we take just the plate in consideration. Place the x-axis along the bottom of the plate and the y-axis bisecting the plate, leaving the origin at the midpoint on the bottom of the plate. The plate presents a shape similar to half of a circle with a radius of 5 feet. For that reason, we'll be using the equation of a circle. The equation of a circle is x minus a quantity squared plus y minus b quantity squared, which is equal to the radius squared. Since a and b provide shifts to the circle, in our case that's going to be equals to 0, giving us the equation x squared plus y squared equals r squared, and by observation we are able to find that the distance from the origin to the x-intercept, it is 5 feet, which gives us x squared plus y squared equals to 5 squared. Solving the equation for y, we get y squared is equals to 25 minus x squared, and finally y equals square root of 25 minus x squared. Now that we have found the equation that will model the submerged object, we are going to redefine the location of the x-axis, moving it to the surface of the water. According to the diagram, the plate is submerged 2 feet away from the surface. Adding it to the radius of the plate, we obtain the total depth of 7 feet. The y-axis represents the vertical measurements, such as the depth and the height of the plate. In order to relate both, we must write an equation in terms of y to represent the depth at each point on the plate. At 90 degrees, y equals the radius, 5 feet, and the total distance from the surface of the water to the bottom of the plate is equals to 7 feet, which can also be expressed as 7 minus y. Because the depth is now defined in terms of y, the width of the plate must also be defined in terms of y. So we come back to this point in here, and this time we solve for x, which gives us x equals the square root of 25 minus y squared. However, the output of this equation only represents one side of the plate. In order to properly reflect the total width of the plate at one point, it must be multiplied by 2, and consequently the function becomes 2 times the square root of 25 minus y squared. By dividing the plate in many small segments, we are able to approximate the area of the section by multiplying the height, y2 minus y1, or delta y, by the width, giving us 2 times the square root of 25 minus y squared times delta y. Now that we have the depth and the area for the plate, we can plug it into the equation for the force, giving us force equals delta times 7 minus y times 2 times the square root of 25 minus y squared delta y. We were given delta as 62.5 pounds per cubic feet. To approximate the force acting on the entire area, we must sum all the small sections. For that reason, we apply the Riemann sum of the end parts, giving us delta times 7 minus y times 2 times the square root of 25 minus y squared times delta y. However, this is just an approximation. In order to evaluate to an exact number, we would have to take the limit as n goes to infinity, giving us the function f equals to the limit as n goes to infinity of the sum delta times 7 minus y times 2 times the square root of 25 minus y squared dy, which it is the definition of the integral. So, the force exerted by the water, it's equals to the integral from 0 to 5 of delta times 7 minus y times 2 square root of 25 minus y squared dy. Since 2 and delta are constants, we can move them out of the integrand, giving us force equals 2 times delta, the integral from 0 to 5 of 7 minus y times the square root of 25 minus y squared dy. And after plugging in the value for a constant delta, we get 125 times the integral from 0 to 5 of 7 minus y times the square root of 25 minus y squared dy.